Yes? Hi, welcome everybody. Thank you for coming to our last but one seminar of the year. It's a pleasure to have here Dr. Ian Dryden from University of South Carolina to tell us a little bit about some of his research work. Dr. Dryden received his PhD degree in statistics from the University of Leeds in 1989. He's been a professor in the Department of Statistics at University of South Carolina in 2009, which basically he joined from being a lecturer and senior lecturer at University of Leeds, and then visiting professor at University of Chicago, and professor of statistics at University of Nottingham, which was his last place of research. And his research interests include many things, including shape analysis, statistical image analysis, medical imaging, spatial statistics, and high-dimensional data analysis. And with all sorts of application to medicine and biology and computer science. He was also a chair, he was a recently appointed chair of the research section of the Royal Society, the Royal Statistical Society. And it's a pleasure to have him here. And thank you for coming. The floor is yours.
Thank you very much. So thanks very much, Hamid, for the invitation, and it's great to be here. I think if I'd have known I was going to be on show publicly via the web or whatever, I would have perhaps dressed a bit more smartly and have a tie maybe. But anyway, you've got me as I am. So I'm going to tell you a little bit about this project to do with Bayesian alignment of molecules, which is the application that we're looking at. And this is something that people are very interested in doing in chemoinformatics and bioinformatics in general, comparing molecular structures. And we want to do some of this comparison using a statistical approach. So I'm going to plan the talk as follows. I'll introduce the area in general, just a little bit about shape analysis and what's special about it. I'll introduce the application of molecule matching, and in particular, I have an application of steroid matching, which I'm going to show you, where we're interested in matching small drug molecules. And then the way we're going to do it is we're going to be using random fields in order to model what's going on and to compare the molecules. So if you want to ask any questions throughout, please don't hesitate to do so, so that I sort of get some feedback as we're going along. Okay, so shape analysis is part of an area of analysis of non-Euclidean data. So by non-Euclidean data, I mean that the distance between our objects under study is most naturally a non-Euclidean one. So there's some sort of curvature in the space which we need to take account of. So a classic example is where you have data observations on a sphere, and here we've got some points, red points observed on a sphere. And we want to be able to do some sort of analysis, statistical analysis of the points that are available. So a very simple thing I might want to do is to find the mean of the points on the sphere, taking into account the fact I have curvature. So if I want to look at the distance between the points on the sphere, a natural distance is the great circle distance from one point to another going along the surface of the sphere. So that would be an example of a non-Euclidean distance. The second example are where we have axes. So we have points on a sphere, but we don't know whether they're sort of pointing outwards in one direction or whether it's completely 180 degrees round in the other direction. So we have unsigned directions or axes in this case. So that's called axial data. And that sort of data crops up, particularly when we're doing things like principal components analysis. We have axes, which are the directions of variability, and those are examples of axial type data. Other examples here, well, I won't go into detail with them, but things like rotation matrices lie most naturally in a non-Euclidean space. The thing I'm interested in is shapes. So we have some pictures at the bottom there of some points in the brain, MR scan of the brain. And if I'm interested in comparing the shapes of the configuration, I'm not really interested in exactly the rotation of the points in the plane or their location. So if I want to remove that aspect, the rotation and location, maybe even the scale, then I introduce constraints into the data, which means that this non-Euclidean distance is most natural. Here's a big molecule, so a protein, and that's like the sort of application I'm going to talk about, where we're interested in comparing the shapes of the molecules to see if they've got something in common. They have a similar function. And then the last one is just an example of a covariance matrix. So if you're describing the variability of several observations, you have a covariance matrix. There's a constraint that it must be positive definite, symmetric positive definite. And so that constraint means that we're lying in a non-Euclidean space is more natural. So this is the whole sort of big area. At the moment, there's a program at SAMSI, at Research Triangle Park down the road, where people are looking at the analysis of objects. And these very much fit in with this framework, all these types of applications. Okay, so what's special about the area of non-Euclidean statistics? It's important to be able to actually specify a distance, and the distance that we choose is in many ways up to us. We want to choose a distance that is natural. So when it comes to my application of comparing molecules, I want to be able to choose a distance that makes sense for comparing my molecules. And then if I have a distance, then I can find how far apart things are by working out the length of the shortest path between the objects. And then if I want to do something a little bit more practical and sophisticated, like describing the variability in my data set, or maybe even just finding the mean and then finding the variability, a common thing is to approximate the space with like a tangent space, a flat space, and then do my analysis there as a practical simplification if I want to. So I also want to specify probability distributions in this space as well if I want to do formal statistical inference. So even defining a mean isn't straightforward, and defining variability isn't straightforward. You know, in many situations, if the data are very spread out in our space, it may be that there isn't a unique mean. So that's very different from Euclidean data analysis, which we're used to, where the mean is defined without ambiguity. So this is one complication. Right. Any questions at this stage? Just do butt in, please. Right. So as a statistician, and I know I have a sort of a multidisciplinary audience here, so I'll try not to emphasize statistics too much, but I think it's inevitable that I will mention statistics a fair bit because that's my background. But we would want to do things like estimating means, hypothesis tests, fitting straight lines maybe to describe perhaps growth, or fitting splines. If something's evolving over time, we might want to fit a smooth path in this space. So there are a whole host of applications and methodology that we want to develop. And the field is fairly immature, actually. There's not that much which is agreed upon and as to the right way to go about things. Even whether how to define a mean still gets people arguing in this field. So molecule matching. I'm going to be considering a situation where in chemoinformatics, people want to compare molecules to see how similar they are. So you might have a very big database of molecules, say drug molecules, and you have one molecule that you know does something that's important biologically. So it happens to bind to a particular protein which helps with alleviating symptoms of a disease, for example. So you've got this drug, and somebody's patented it, and it's very well protected. And one of the things that people want to do is to find something that's similar but not exactly the same, which does the same job. So one task is to try and find from a big database of drug molecules. You know, these databases are huge, all the possible arrangements of atoms in molecules. Find something which is similar in terms of maybe the shape, the geometry is similar, and then maybe it will do a similar job in terms of binding to a protein. So I'm going to be looking at my molecules to see what similarities they have, the geometrical similarities of the molecules, and that will help me to compare molecules and whether they're close or not. So geometric similarity is key. It's not the only property. Often the charge that you have on the surface of the molecule is important, and the actual types of atoms are important, obviously. But geometric similarity is also very important. But this task of comparing molecules is actually very difficult. There's a lot of people want to be able to do this and are indeed doing it. You can imagine that pharmaceutical industry would be very interested in this. And there are various approaches for doing it, but it's not easy. It's very difficult, extremely difficult. So there's still room for trying to develop methods that compare the shapes of molecules. So here's the task. Here's the data set. There are 30 steroid molecules here, and what I've done is I've plotted them. It's just the XY view. They're actually three-dimensional drugs, but they're fairly. There's a clear axis running through them, so that I can plot them in this view, and then you can compare them. So my question, first of all, is for you to tell me which ones are similar. Look at them and see if you can see any similarities. Just use your eye to look over them. I think the first thing I thought of was, well, they're all exactly the same. You know, they've all got these 4 rings. You know, that's something that they all have. So 1, 2, 3, 4, and a smaller one there with just 5 atoms, and then 3 here with 6. But then when you start to look closer, you see that the molecules, you know, they've got, that's there and that's not present in this one. There are bits hanging off sort of, you know, out here that maybe are not present in some of the other ones. You know, you look around, you can see there are bits where they're present, and like here we've got an extra bit up here which we don't have here. So there are differences. 17, some of them are very similar. 17 and 18 look very similar, I agree. Yeah. So now the thing about these steroid molecules is some of them bind very well with a particular protein. Some of them don't. They're hopeless, don't bind at all. Yeah?
In plain though, right?
No, I'm going to do it in 3D.
Okay.
Yeah, this is purely just so that we can...
For illustration.
Yeah, for illustration. It's just one way of looking at them. Yeah, it's all going to be 3D. Yeah. So, yes, some of them bind very well, some of them don't, and some are the sort of halfway between. They have half medium binding activity. And so it's important to be able to understand why they differ geometrically, and can we summarize the geometrical features that will enable me to say that it's going to be in the high binding affinity group or the low binding affinity group. Now, what have they got in common? So, yeah.
And it's
Sorry.
maybe more like a biology question, I'm not sure.
No, yeah.
So when you have these little kind of hanging off bits,
Yeah.
if you have like multiple instances of the same molecule,
Yeah.
is it going to be shaped the same way, or will they be hanging like in a lot of different directions?
Yes, that's a good question. So these molecules, all molecules move around, okay? So the atoms move around. These are pretty rigid, and actually steroid comes from the Greek term, I've forgotten exactly what it is, stereos or something like that, which actually means rigid. So they're quite rigid molecules. But you're right, these bits here may well have like some rotatable bonds, and there may be a little bit of movement around there. Okay. However, for the purposes, because they're of my analysis and because they're pretty rigid compared with most molecules, I'm actually going to treat them as rigid. Okay, so yeah. But that's a good point that if there are rotatable bonds, maybe one should allow them to be able to rotate around a bit. Yeah. Yeah. Yeah.
So, how do you normally establish that for at least rigid molecules that the geometric property is the key here?
Right.
It might be, we can also assume, I mean, that because they differ in atoms.
Oh, yes. Yeah, no, there are other aspects as well, the charge and the atom type, for example. Well, this is part of what I'm about to do, yeah. I mean, in many situations, the geometry is key. I work with, this is actually work joint with chemists back at Nottingham. And, you know, they say that, you know, geometry is very important. It's not the only thing, but it is an important thing. And they were particularly interested for this problem in looking at the geometry to see why the three groups are different in terms of the geometry. Yeah. So it could be we do this analysis and there's no difference geometrically.
On similar atoms.
Yes, but yeah, they do have different atoms. Yeah, they have different numbers of atoms. They have, you know, some different types. Some of them have, you know, more oxygen ones hanging around, and yeah. I'm looking at the whole thing, and I am going to take into account the atom type and the charge. There's a partial charge associated with each atom. Yeah. Yeah. So all these things are going to be taken into account. So if we just look at two of them, and these are the first two alphabetically in the data set, then I actually have, from X-ray crystallography, we have the coordinates of the atoms in their rigid position, and we have the type, and we know like the van der Waals radius is associated with the actual type of atom. We know the charge, partial charge at each atom as well. But one thing that's different from this shape application, say comparing the points in the brain that I mentioned briefly at the beginning, is that I don't know which atoms match with which particularly, okay? I'm just given the atoms. They can be ordered anyhow in my database. I don't know which ones correspond. So there's no given correspondence, although in this application, the rings are a good way to start the correspondence, but I haven't been told which ones match up. And that's what makes it difficult. We don't know which ones match up. If I had the same number of atoms and I had them all labeled 1, 2, 3, 4 up to 10, I could do fairly standard shape analysis on that. But I don't have that. So what I actually do have then is the coordinates of my points. So k points in Rm. And so m is 3 for us, and k is around 50. So it's 50 or 60 in this one. And these are small molecules. Okay, and now let's say we have a second configuration which has a different number of points, L, in m dimensions. And I want to see how close together they are. I'm trying to devise a distance of similarity at this point between the two molecules. And I'm going to introduce a labeling or match matrix, which is of size k by L, which is going to tell me which points match up with which ones in the other molecule. So it's going to give me the correspondence between one to the other. And this is one of the things I don't know. I don't know this labeling matrix, and I want to be able to estimate it from the data. And if I have this labeling matrix, I know that not all the points are going to match up because I have a different number in each of the molecules. So I'm going to have some parts which match, and I'm going to call that xm, and some parts that don't match, which I'll call xn, non-matching. So I'm not going to have too much notation, but I thought I'd just introduce a little bit here, and then you know, some of the model as well will perhaps be a little bit more understandable. So a very simple example where I have 4 points in one configuration and 5 points in another. And this is just in 2D, just for illustration. It's just a very simple toy example. And I'm going to have, they're numbered according to, if I was given these coordinates by someone as the data, they come with numbers 1, 2, 3, 4 for the first one, the red configuration, and 1, 2, 3, 4, 5 for the blue one. So this is what they're given to me. And I want to be able to estimate this labeling matrix. And this labeling matrix, in this case, it would seem reasonable that if 1 and 3 were matched up. So red 1 matches to blue 3. So to indicate that, I have a 1 here. So going from the red 0.1 to blue 0.3. And then red 2 seems close to 5. So I'm going to have 2 to 5 here, 1 there. 3 doesn't seem to be near anything here. So that's going to be a non-matching one. So there's no 1 in here. It's just a load of zeros. And 0.4 in the red seems to match up quite well with 0.1. So that would be an example of, in this case, a fairly sensible labeling matrix. And then there would be 3 matching points in the 2 configurations. And then once I have that lambda here, I can then compare the shapes of those matching configurations. Right, so that's just a simple example. But if I have, 50 or 40 points, I want to match them together. I want to be able to estimate this labeling matrix. And if there's no match for a point, then there will be just a load of zeros in a row. Okay, so that's going to be the task. Now, if I have matched points, then I can use what's become a fairly standard part of the toolkit of shape analysis for matching landmarks, Procrustes analysis. So if I've got my labeling and I want to match my matched points in xm to the matched points in μm, then I can rotate xm, which is that capital gamma, a special orthogonal matrix, which is a rotation. I can translate it with the other gamma, and then I can get them as close as possible by minimizing the square Euclidean distance. So here's just an example from biology with some points on a skull. And I want to match one to the other or this one here to the other by rotation and translation to get them as close as possible. So that can be done just with singular value decomposition and straightforward bit of matrix algebra. And so the optimal rotation here is just formed from this U and W from the SVD there. And then the tangent coordinates for this situation are the difference between the match configuration and the one you're matching to. So that's fairly routine now. This would be how you can compare things when they're matching. But for us, we don't actually know what the lambda is. That's the problem. So we need to be able to infer that as well somehow. So our model is a Bayesian, or built around a Bayesian approach. So where we will have a term for how well the points match together, which is a likelihood term for the goodness of fit of the matching points in one configuration to another. And then how close they are will be just with some normally distributed errors. Okay, so we're going to have a Gaussian distribution for this V. The V is the tangent coordinates that I had at the bottom there. So once they're matched, then the sort of errors in matching here will have a Gaussian distribution. So that's going to be part of the model. And then I've got the unmatched points as well, which also will contribute to the model somehow. But I haven't really got any information about where is a good place to put the unmatched points. So I'm just going to say they're uniformly distributed around, in a bounded region around the molecule. Okay? So that's the second part of the model. And then, because I'm going to do it in the Bayesian way, I will introduce a prior term, a prior distribution for the parameters. The parameters here are the lambda, the matching matrix, and the sigma squared, which is the error variance as well. So I won't dwell on all the details of these distributions, but I'll try and give you the idea. Okay? So the idea is I've got a model for how close they are matching together for the matched part. Another model just saying the region in which the unmatched points are, and then I say in advance a distribution for the parameters, the lambda and the sigma squared. And I'm going to assume that I don't really know much at all about the lambda and the sigma squared, that they have diffuse priors or not much information. And then I can do inference on all these parameters using Markov chain Monte Carlo simulation. So it's not easy to simulate from or do inference, but you can simulate from the posterior and do your inference. Right, now this was actually done a few years ago, and there were several people who have done similar stuff. Scott Schmidler at Duke, who did something pretty similar to this as well. Green and Mardia did something as well, and myself and the chemists implemented this approach as well. And it seems to work okay. It works pretty well in this situation, but it's fairly time-consuming. But for example, if you start off with these red and green ones, which are these first two, and then this MCMC is like an iterative computational simulation algorithm, which is simulating values from a posterior distribution of the match matrix and the sigma squared. As you let it run, the molecules will hopefully come together, and this is the end result of a successful run. What happens sometimes is they come together and they don't match up in what would seem a very sensible way. They sort of back to front, like, you know, and you can tell they're not matching up well because the sigma squared has a very big value, and it sort of gets stuck around there. So these are a couple of views at the end of this procedure. I've just drawn some circles round. This is the view we're used to looking at of the molecule. Circles around pairs of atoms in the red and green molecule which are actually matched up. So the bulk in the middle is matched up, and bits on the end are not matched in this particular example. This is just another view here. Okay, so that's where, you know, we did a reasonable amount of work on this, but it's quite discrete, this matching, that things are either matching or not, and you know, it's quite difficult to actually to do the inference. It's not straightforward. And also we have this extra information about charge, which I haven't used. There's other things I haven't used. So we wanted to investigate a second approach, which actually is more continuous and uses, rather than just the points, uses a random field of model. So that's what I'm actually going to talk about, which is the main part of this. So the field matching is where it's the same problem, but the points now are regarded as located in a continuous field, in a random field. So I have k points located in a random field. So at each point you have a measurement, which may be a charge or something else. Okay? So k points in this continuous field, and I'm going to assume something about the covariance function between different points. So points that are close together you would expect would have more similar values than points that are further apart. So So this is my basic model is going to be that the points are located in a random field. And what I'm going to do is predict my field from the points that I have available. So if you look at this, this isn't just a 2D example here, but I've got some points here. Each one of them has a measurement associated with it, like a charge, for example, or the radius, or some other geometrical measurement. I can predict in between the points the measure using what in spatial statistics is called kriging. So it's just interpolation between the points. So I've got my atoms, and then I'm going to say that rather than just having observations at this point, they're observations from a continuous field, and I'm going to be able to estimate that everywhere. So interpolate between the points on the in the field. Okay, so algebraically we don't really need to go into the details here, but you specify a covariance function here, which the predicted value at any point, even away from the points where we have observations, is given by just this linear combination here, where it depends on how far away it is from each of the points. Now, this has actually been considered in the chemistry literature quite a long time ago, in fact, where they did something similar, where you get a field that you imagine your molecule. It's not just discrete points; it's a fuzzy cloud of electrons. It really is a continuous object anyway, not just a set of points. And then, so you get one field estimate for one molecule, and then one for another one, and then you try and find the location and rotation that'll match them up as close as possible. Okay? And so they suggested using this index, which basically tries to maximize the correlation between the two fields to put them in position so that they have as much in common as possible. So that would be using an L2 norm. So you just are integrating the product of the two predicted functions. So that's the Carbo approach, which has been used in chemistry for quite some time. And then if one uses another similar sort of algorithm, which uses this particular covariance function, the Gaussian one, then one can actually you don't need to do the integration numerically, which the Carbo people did. So you can actually work out the overlap without having to do expensive numerical integration. So the naive approach to this is you've got your two predicted fields, and then you've got to numerically integrate the product of the two fields in all possible positions. Right. Okay, so this is the approach we took. So this is the main contribution of this talk, and that would be that we wanted to develop a method for comparing the fields which doesn't depend on this Gaussian covariance function, which has flexibility in the covariance function. So we say that our predicted field would be a member of a reproducing kernel Hilbert space, which just means I can express it in this form as the sum of alpha I times this covariance function here, and the inner product in this reproducing kernel Hilbert space has this nice simple form where it's just a double sum over all pairs of points. Okay, so you don't need to do any integration. This is the inner product between the two functions. Just depends on the points. So I can actually easily find the inner product between two functions in this way. So all I need to do is specify my sigma, and I know where the points are, and then I can get this expression. So just like the carbo index was like a correlation, this is what we're going to do. So we have the two predicted fields from the two molecules, and I can work out the inner product in this reproducing kernel Hilbert space, and then I just normalize so that the thing lies between -1 and 1. So that's a measure of how similar the fields are, and doesn't require any integration. And then to actually match the two up, I want to get the fields so that they match together in terms of rotation and translation as close as possible. So that needs to be done. So I'm going to do that. And then if I, as well, instead of working with correlation, I could work with like a discrepancy or distance, just transform it onto the positive real numbers. So that sounds promising. That sounds a good way to go. But one thing to bear in mind is that these molecules, you don't have to have the whole lot matching up to have the same function. If we look at these two much bigger proteins, which have very similar function, this bit here doesn't have a corresponding part here, and yet the rest of it all matches up very well. So I would be interested in seeing which bits of these two fields are very similar, ignoring some bits that are different. Okay, so I'm looking for common parts of the two fields. So I'm not too worried about bits that don't match up. So that is an extra part that I can introduce into the inference. That I want to actually include that. And I can actually do that fairly straightforwardly in this case by, and this is the last part of the model, by introducing some what I call mask vectors, which tell you whether the points in the data should be present or not. So you have a mask vector for molecule A, and basically it just says, shall I use the jth point or not, or shall I just not include it in the matching? And likewise for the other one, shall I include that point or not? And then my predicted field is done either with or without each of the points. No, I need to estimate that. Yeah, so I need to determine that. Yeah, so I don't know the mask vector. That's part of the inference. Unlike the example at the beginning or the first part of the talk where I was looking for correspondence, this is just saying whether they're present or absent. So we're not making any sort of link between the two. We're just saying whether to include or not. Okay, so the method then, after I've done this, the method is very similar to the one that I used before. I just use a Bayesian model with Markov chain Monte Carlo simulation. So my distance here is this one, this discrepancy measure. It depends on the relative rotation, translation, and then the mask vectors, whether they're present or absent or not. The points present or absent. So this is my likelihood, and this here, this d, is my distance between the two molecules. And then I need to introduce a prior term. And so this turns out to be a very important parameter is a prior term to tell you whether there should be a large number of points included or just a small number of points. So this is a hyperparameter. The larger this is, encourages more points to be in. The other two are not such important prior parameters, but that one is. So if you want a lot of points to match, then the xi parameter needs to be big. If you don't want that many points to match, then it's smaller. Okay, so that turns out to be very important. Okay, and then the uniform prior. Well, that doesn't really matter. There's just the prior on the rotations depends on how you parameterize your rotation matrix. There's no way of parameterizing a rotation that doesn't have some singularities in it. So this is just the way we did it, using 3 angles, Euler angles. at the end of the day, I use Bayes' theorem. I have a likelihood, I have a prior, and then I want to simulate from the posterior, which will give me inference about the parameters that I don't know. Right, so we did some simulation studies just to see if it worked first. We simulated some points. These are actually 2D simulations, and we've done 3D ones as well. So you simulate a field. Here's a field, and then take some points out of the field, and then put them into arbitrary rotation locations, and then see if you can match them back again. So it's like a simulation study. You know what the true position should be, and then we're trying to see if we can get it back, basically. If we can't get it back, then it's hopeless. If we can't do the simulation study, then it's no good at all. But it does work okay, but you can push the parameters to see when it starts to go wrong. So the first case is where I simulate a field here, and then I take some points. Green ones are for one configuration, which are uniformly, and then the red ones, which are close by to the green ones. They're uniform within a box of size 1, I think it was, or a 3 by 3 neighborhood. So the red ones have to lie quite close to some green ones. So that's on the left. So that's easier. We should be able to do that one pretty easily. This one is harder, where the red ones are allowed to be further away. And we want to see if we can still match up these configurations after we throw in a random rotation translation. Can we get them put back together using the information in the points? And so we added some noise as well, which is the like measurement error. And we also added some contamination points that shouldn't match, that were just thrown in there as well. Okay, so that's what we did. And then the details don't matter about parameters and things, but we basically started off with a very large, smooth estimate of the molecule, which was this 0.6 here, so that the molecules are easier to get roughly in the right position because there's a large amount of smoothing going on. And then we reduce the smoothing so that it gets less at the later stages. So anyway, it seemed to work okay. This is just the sort of output you get. You get Markov chain Monte Carlo output. You just get a chain of your parameter estimates as you're going, or parameters from the posterior as you're going through the simulation. And you hope that it all settles down and becomes like stationary looking, and then you're simulating from the posterior distribution, and you can look at things like posterior means, posterior modes, which are your estimates. Right. So this is an example where the start position is on the left. I knew what the true position would be here, and then after the MCMC scheme, it ended up here, which is very similar to that one. I haven't put them on top of each other. It's not exactly the same, but it's very similar. So I wanted to see how often this works. Okay, so basically, if the problem's easy enough, then we ran lots of simulations, and 100% of the runs out of 100, I think it was, were successful. But then as you start to make the problem a bit more difficult, you make so they don't match up so well in the first place, then you start getting some failures of the algorithm. And then you can really push it. So you introduce, like, smaller number of points is more difficult. And then with smaller number of points and a larger neighborhood, then only 1 in 5 I could actually get this right. So you can understand when the thing's going to not work and when it does work. But the last thing is to actually really apply it to the data. That's the whole point of this. So move forward to the steroids. So I've got the steroids. I want to predict the field. I want to match together. So I used this Gaussian covariance function and did the MCMC, and it actually does work reasonably well, and I'll carry on through that. And then I want to see if I can see shape similarities between the high, intermediate, and low binding affinity to this protein, this corticosteroid binding globulin receptor. Okay, so I want to see if my shape measures are able to distinguish the high, intermediate, and low. So one thing we did was we ran all possible pairs of matches between all the steroids in the database, and then we did some cluster analysis based on the dissimilarity from our method. So here is from the posterior mean, and then what we do is we look to see how close together in terms of the dissimilarity measure the observations are, and the ones here are all, I'll just see which way round they were. I think the one are the high binding affinity, the 3s are the low binding affinity, and the 2s are in between. So this is one approach, and then here this is another approach, the posterior mode. And if you actually look at this one in particular, the 1s here and the 3s have really been very well separated. The low binding and the high binding have been very well separated by this distance, which is this field similarity measure. And the 2s are sort of mixed in between. And I haven't told it what the labels are at all. I've just labeled them after I've done the clustering. Okay, so it's picking up picking up that the 1s are more similar to each other, the 3s are more similar to each other, and the others are in between. So it is actually doing something sensible. And then once you've aligned them, you want to be able to see where they differ. So there's an extension to multiple alignment. The previous one was just in pairs, but you can match everything together in one go. And then we want to try and see if we can spot where the differences are between the molecules. So this is at the last stage, is to try and see, okay, they're different. Where are they different? So we looked at where's the middle, low versus high class. So you get all the low ones and the high ones and match them all together. And then I've shaded in some areas where there was a t statistic was high, telling you that they were very different at that point. So there are between the high and the low, you've got some differences up one end and up the other end. The low and the medium, the differences are more around here, and the medium and the high is more up that end that do it. So you're getting an idea of where they differ in the different groups, just using simple t statistics. Right. So I've included quite a lot here. I know that, but I've told you about the steroid molecules and two approaches to matching. One based purely on the points, and then the second one, the more recent work on the fields. And I think the fields one gives you slightly better clustering actually than the points only one, which I didn't show you, but it is a bit better. I think it's taking more into account. Just a couple of slides to wrap up with. I think this area itself is very interesting. There's a very large number of applications. Chemistry and bioinformatics is one, but we mentioned sort of landmarks and brains as another. Covariance matrices, which is what that middle one's supposed to be. Often people normalize the data. This comes from a microarray where it's standard to normalize that you divide through, say, by the sum of the squares of all the observations. Or that in itself has caused a constraint, which means our data are now more naturally non-Euclidean rather than Euclidean. And I think it's a bit corny having a picture of a bridge, but I think they're very important, the interlinks between the different disciplines, and the fact that I'm here not visiting a statistics department, for me is very interesting to come to another department I'm looking forward to speaking with people afterwards, learning about the things you're working on, and I think this is how we learn and make progress. And this area of shape analysis is so interdisciplinary and requires expertise from different areas. Does anyone recognize that bridge? I would be very surprised if you do. No. It's in Columbia, actually, in South Carolina. So I drive over it each way every day. So I see a lot of that bridge. So, but it does remind me that it's good to link together. So that's the last slide, I think. So the two papers, the earlier work on the atoms there and the more recent stuff. And thanks to various sponsors. And thank you very much to you for listening to me. Thank you. Yeah.
So when you're designing the field on the molecules,
Yes.
Does it require a lot of domain-specific knowledge to design the field?
So you mean the covariance function in particular, which that's the key thing. So the covariance function, what range of smoothing we should use, and what type of function.
Given a molecule, you compute a field on the molecule, right?
That's right. So we've used a field which would not be probably very realistic. It's a simple field. So where we're actually assuming a stationary field, which is not actually true, really. The molecule, you know that as you go away from the molecule, a measure like charge will just drop down to zero. And so,
informed by the chemical properties of the atoms at that position, or?
To some extent, I believe, yeah. But the other aspect of the field, which would be the van der Waals radius, which is like the radius of the shell, that's completely determined by the atom type. Okay, so I think the charge is not so related. It's more that radius is. So the field that we use uses the charge and the atom type as well. Okay, so this van der Waals radius, we use both aspects in our field. We use like a bivariate field in the cluster analysis. Yeah. So we've used something which is probably physically not quite realistic, but it's enough to be able to get an overlap and to find similarities. I think you would need some sort of non-stationary field if you were going to do it very realistically. But it does seem to be good enough, at least for here. Yeah. Yeah.
I'm not sure if it's been applied, but it seems like you would expect this method to perform well in like a classification type of problem where you're given a molecule, a steroid, and you know that it's from one of these 20
Right. Yes.
ones.
Yes. Yes. It should.
Maybe like that would kind of show this is really good at identifying.
Yes.
Each.
Yeah. Yes. So I think, in this particular data set, I've got 31 steroids, and that's all we've got. And so we've used them all. So it would be hard to actually sort of get a fair sort of classification type measure. But in the clustering, there was no knowledge used at all there. But yeah, if you had if I was to build it up without knowing a couple of them, and then try and classify those, it should do pretty well, I think. Yeah, but it's better to have really genuinely new ones to put into classification to really test it. Yeah, that's what they're interested in. Yes. Yeah, that's right. Yeah, but no, you're right. I think. Yeah. I think that's a good point. Yeah.
So I was thinking whether this would be a good idea, or whether there's some work done on this. For example, if you have some training data, like these data sets are different, then could you find the optimum field which could actually separate them most and actually see how this field can be?
Yeah, that's a good question. Yeah. Yeah, I think so. I've built up the model by sort of the optimal fit to the data, basically, by optimizing this posterior. But rather than that, trying to use the class labels to get the best discriminating field. Yeah, and you would get different estimates. Yeah.
Those fields in the first place, too, right?
Yeah, yeah. No, I think that's a good extension of this work, actually. Yeah, it's something good to look at. Yeah, which I certainly haven't done. Yeah, yeah. Yeah.
Uncommon to ask is that because for molecules, especially when it's treated as drug, there's functional part for it and non-functional part for it. So
Right.
when you do the matching, can you just add more weights to the functional parts so that makes the matching more practical?
So sorry, what do you mean? Add more ways?
Yeah, I mean, because
weight.
More
Weight.
weight.
Oh, weight. Yes. Sorry. Yes. Yes. Definitely. Yes. Yeah. So at the moment, I haven't included any sort of weighting between the points. But you're right. You can introduce that extra knowledge into the model. That's a very good point. Yeah. So if you have, that's the great thing about the Bayesian framework, that you can build in this extra knowledge. And you, for example, in the prior, you could say, I expect these points to be in, these parts, or these parts, these are unlikely to be in, so I'll a priori downweight those. But if they turn out to be important, they can still come in into the model. But yeah, so that would be tailoring it with the prior, I think. Yeah, yeah, that's good. Yeah.
I'm sorry, excuse me, I'm not quite clear. How do you determine the mass vector? The mass vector you mentioned in the second part.
Okay, so the mass vector is purely
purely 0 and 1s, right?
0 and 1s, yeah. Which so at any stage of the algorithm, I have a vector which has 0s and 1s, and if it's a 0, I don't include that point in the field interpolation. Okay, and if it's there, it is included. Okay, yeah.
But so you are doing an optimization. And you determine the mass vector.
That's right. So that's this Markov chain Monte Carlo algorithm. So basically, you start off with a guess. Just stick all 1s in, for example, to start with, and then at each iteration of the algorithm, you flip a 1 to a 0, and then you have a rule for deciding whether to accept this flip or not. Okay. So it's the Metropolis-Hastings algorithm. So that's part of the algorithm. So as you go along, if it's beneficial to flip to a 0 to drop it out, you will definitely accept it. If it makes it worse, you sometimes still accept it. Okay.
Possibilities.
Yes.
It looks like you're searching all the possibilities.
Well, yes. So the algorithm will lead through the space, hopefully. To a high density part of the space, but the actual space is enormous. So you're not going to be able to search through the whole space. You're not going to be able to run this long enough. Okay, so we found that it seems reasonable, but it's not. We're not actually optimizing. We're simulating, which is approximating. You hope with MCMC that you end up near an optimum at the end. But it's quite possible for the algorithm to get stuck and not get there. But you can tell whether you're stuck close or not by the distance measure. If it sort of looks too big, you start again. Yeah, just from another random position. Yeah.
For like meta parameter on the number of 0s and 1s.
Yes. Yeah, that's right. Yeah. So that was key, and you need to play with that a bit because. If you insist on a very large number of matches, then you've got to. That's balanced with it won't end up matching that closely at the end of the day, and if you allow a lot of them to be dropped out, then you end up keeping only 2 or 3, and they match up really well. So there's nothing in the data to tell you about which of those 2 you want to do, and so you have to tell it. Oh, I prefer to match as many as possible. Or not. And here you need to be matching a reasonable number, or else it just becomes sort of silly, really. Yeah. Yeah.
It seems, of course, the computational complexity is a big factor, right?
Yes,
And,
yeah.
But then the next question that comes up is, have you considered perhaps approaching the problem with a hybrid approach in the sense where you would actually include as a first filter, as a first pass to your classification, like a topological filter, right?
Right.
In other words, do these guys agree at the very least at a topological level? And then let me search further for the geometry.
Yes, yeah. I think that's good, actually. And that's, in a way, we found that we had to do, not quite what you're saying, but we had to match things crudely to start with and then refine it later. So our smoothing was really big smoothing to start with. That's not quite what you're saying, I know, with the topology. But, but a crude thing, yeah.
You look at the number of holes or what have you,
yeah.
and you say, okay, these cannot be the same because
because of that.
The topology is not even the same. Right?
Yes. So although we didn't do that, but that basic idea of looking for very big features and is very important. Yeah. If you try and just go in for the detail, you just miss it. Yeah. You have to go coarse first, and then to the fine tuning it later. I think that's very important. And so I think what you're suggesting with bigger molecules particularly would be really important. These are very small ones, but bigger ones, there are the topological features will be more important. Yeah, and the computation will be even much more difficult there. So it'd be even more important. Yeah.
We do a lot of topogeometric stuff.
Yeah.
It turns out that actually it does. A hybrid approach does simplify things.
I can bet. Yeah.
Because it basically reduces your search space. Right off the bat.
Yeah. Okay. And so then you end up in the right place roughly. And I can imagine that. Yeah.
Any other questions? Well, if not, let's.
Thank you very much. Yeah. Great questions. Yeah.